Thanks a lot for having me here. Today, I'm going to talk about neural rendering. Because rendering is such a massive topic, I'll start with some clarifications. So as far as this lecture goes, rendering can be both a forward process and an inverse process. The forward rendering computes an image from some 3D scene parameters, such as the shape of object, the color of object, the surface material, and the light source, etc. Forward rendering has been one of the major focus of computer graphics for many years. The opposite of this problem is the inverse rendering. It studies the problem that given some images, we are trying to work out what are the 3D scenes that was used to produce this image. And the inverse rendering is closely related to computer vision with applications such as 3D reconstruction and motion capture, etc. Forward rendering and the inverse rendering are intrinsically related because the high-level representation of a vision system should look like the representation using computer graphics. In this lecture, I'm going to talk about how machine learning can be used to improve the solution to both of these two problems. But before we dive into neural networks, let's first take a very quick tour to the conventional method. This is a sort of a toy example of ray tracing, which is a widely used forward rendering technique. Imagine you are inside of a cave. The red bar is a light source, and the grid is the image plane. Ray tracing works by shooting rays from an imaginary eye to every pixel in the grid, in the image grid. And it tries to compute the color of the object and the ray that you can see through the ray. In this case, the ray directly hits the light source. So we use the color of the light source to color the pixel. However, more often than not, the ray will hit some object surface before it bounces into the light source. In this case, we need to calculate the color of the surface. The color of the surface can be computed as the integral of the instance radiance. However, this is very difficult to do in an analytic way. So what people normally do is to use multicolor sampling, which generates random rays within the integral domain and then compute the average of these rays as the approximation of the integral. We can also change the sampling function to approximate surface material. This is how we can make the surface look more glossy or rough. Most of the time, a ray needs multiple bounces before it hits the light source. And this soon develops into a recursive problem, which is very expensive to do. So there are many advanced ray tracing techniques have been invented to deal with this problem, which I'm not going to talk here. But the general consensus is ray tracing with multicolor sampling is very expensive because of the very high estimated variance and the low convergence rate. For a complex thing like this, you need hundreds of millions or maybe billions of rays to render. So the question we ask is whether machine learning can be used to speed up this process. And the answer, as we will see later in the lecture, is yes. But before we dive into the answer, let's quickly switch to the inverse problem for a moment. So this is a classical shape from stereo problem, where you have two images of the same object, and you try to work out the 3D shape of the object. You do this by first finding the similar features across two images. Then you can compute the camera motion between the two photos. The camera motion usually is parameterized by a rotation and a translation. With this camera motion, you can work out the 3D location of these features by triangulation. More cameras can be brought in to improve the result. And the modern method can scale up to work with 1,000 and even 100,000 photos. This is truly amazing. However, the output of such computer vision system is often noisy and sparse. And in contrast, computer graphic application needs very clean data. It needs razor-sharp details. So oftentimes, humans have to step in and clean the result. And sometimes we even need to handcraft from scratch. So every time you hear the word handcraft nowadays, it's a strong signal for machine learning to step in and automate the process. So in the rest of the lecture, I'm going to talk about how neural networks can be used as a submodule and end-to-end pipeline for forward rendering. And also, I'm going to talk about how neural networks can be used as a differentiable renderer that opens the door for many interesting inverse applications. But let's first start from the forward rendering process. As we mentioned before, Monte Carlo sampling is very expensive, and this is an example. On the top left, we have the noisy rendering with 1 sample rate per pixel. And then the number of samples doubles from left to right and from top to bottom. As you can see, the result also improves. But at the same time, the computational cost also increase. And I'm going to make a very fuzzy analogy here. Most of you should be familiar with AlphaGo by now, which uses a policy network and a value network to speed up the Monte Carlo tree search. For those who skipped some of the previous lectures, the value network takes the input board position and predict a scalar value as the probability, the winning probability. In essence, it reduces the depth of the tree search. Similarly, the policy network takes the board position as input and output a probability distribution for the best next move. In essence, it reduces the breadth of the search. So the analogy I'm trying to make here is we can also use a policy network and a value network to speed up the Monte Carlo sampling for rendering. For example, we can use a value network to denoise the rendering with low sample per pixel. Basically, it tries to predict the correct pixel value from some noisy input. As far as policy network goes, we can use a network to generate a useful policy that smartly sample the rays so the whole rendering converges faster. Let's first take a look at the value-based approach. This is a recent work we did for denoising Monte Carlo rendering. On the left, we have the noisy input image sampled at 4 samples per pixel. In the middle is the denoising result. On the right is the ground truth reference image rendered with a 32K sample per pixel. It takes about 19 minutes to do on a 12-core CPU. In contrast, the denoising result only takes about a second to run on a commodity GPU. So there's a very good trade-off between speed and quality. The whole network is trained end-to-end as an autoencoder with 2 loss. The first loss is the L1 loss of the VGG feature of the output image. The second loss is the GAN loss. The GAN loss here is obviously trying to retain the details in the output image. So this is a side-by-side comparison between the result trained with and without the GAN loss. Denoising natural images has been studied for a long time, but denoising Monte Carlo rendering has some very unique point. The first thing is we can separate the diffuse and the specular components and run them through different paths of network, and then merge the result together. And this tends to improve the result a lot. Secondarily, there are some very inexpensive byproduct of the rendering pipeline that we can use to further improve the result, such as the albedo map, normal map, and depth. This byproduct can be used as an auxiliary feature that generates a context where the denoise should be conditioned on. However, how to fit this auxiliary feature into the pipeline is still pretty much an open research question. The way we did in this paper is something called element-wise biasing and scaling. The element-wise biasing takes the auxiliary features and run them through a bunch of convolution layers and add the result into the input feature X element-wisely. One can prove this is equivalent to feature concatenation. Element-wise scaling runs element-wise multiplication between the auxiliary features and the input feature X. The argument to have both scaling and biasing here is they capture different aspects of the relationship between 2 inputs. You can think element-wise biasing is sort of an OR operator, which checks if a feature is in any one of these 2 inputs. In contrast, element-wise scaling is an AND operator, which checks whether the feature is in both of these two inputs. So by combining them together, the auxiliary feature can be utilized in a better way. And this is a denoised result taking noisy input sample data at 4 RAY per pixel. And we compare our result with alternative method. In general, our method has less noise and more details. Now let's move on to the policy-based approach. I'm not going to cover the entire literature here, but I just want to point you to a very recent work from Disney Research, which is called the neural impedance sampling. So the idea is we want to find for each location in the scene a very good policy that can help us to sample rates smartly and reduce the convergence time. And in practice, the best possible policy is actually the instant radius map at that point, because it literally tells you where the lights come from. So the question is, can we generate this instant radius map from some local surface property through a neural network? And the answer is yes. Just like how we can nowadays generate images from random input noise, we can also train a generative network that generates this instant radius map from some local surface property, such as location, the direction of the incoming ray, and then the surface normal. However, the catch is such mapping from the surface local property to the instant radius map varies from scene to scene, so the learning has to be carried online during the rendering process, meaning the network starts from generating some random policies and gradually learns the scene structure, so it's able to produce better policies. And this is the result. On the left is the conventional ray tracing. On the right is the ray tracing with neural impedance sampling, which converge much faster, as you can see here. Okay. So far, we have been talking about how neural networks can be used as a sub-module for forward rendering. The next, I'm going to talk about how we can use neural networks as an end-to-end pipeline. Remember, we talked about ray tracing, which starts from casting rays from the pixel to the 3D scene. This is so-called a image-centric approach. This approach is kind of very difficult for neural networks to learn because, first of all, it's recursive. Secondarily, you need to do discrete sample, which is very difficult to do analytically. And in contrast, there's another way of doing rendering, which is called rasterization, which is object-centric. What it does is, for every 3D point, you can kind of shooting rays towards the image. And it only needs to shoot one primary ray, so there's no recursion. And you do not need to do any sampling. So this turns out to be easier for the neural network to learn. And the rasterization contains 2 main steps. The first step is for every 3D primitives, you kind of project the primitives to the 2D image plane and then impose them onto each other based on their distance to the image. So in this way, the frontmost surface can always be visible in the final rendering. The next step is to compute the shading. Basically, it calculates the pixel color by interpolating the color of the 3D primitives, such as the vertex color. In general, rasterization is faster than ray tracing. And as we mentioned before, it's easier for neural network to learn because it does not have recursion or discrete sampling process. All sounds great. Apart from, there's another catch, which is the input data format. Here are some major mainstream 3D format: depth map, voxels, 3D point clouds, and mesh. And some of them are not very friendly to neural networks. And my policy network tells me I should avoid them in this lecture. So anyway, let's start from the depth map. This is probably the easiest one, because all you need to do literally is to change the number of input channels for the first layer. Then you can run your favorite neural networks with it. And it's also very memory efficient, because nowadays the accelerators are designed to run images. Another reason for depth map to be convenient to use is you do not need to calculate the visibility because every information in the depth map is already from the frontmost surface. All you need to do is to compute the shading. There are many works in rendering depth map into images or the other way around, and I'm not going to talk about them in this lecture. So let's move on to Voxels. Voxel is also kind of friendly to neural networks because all the data are arranged in a grid structure. However, Voxel is very memory intensive. It's actually 1 order of magnitude higher than image data. So conventional neural networks can only run voxels of very low resolution. But what makes voxel very interesting to us is it needs to compute both visibility and the shading. So this is a very good opportunity for us to learn an end-to-end pipeline for neural rendering. So we try this end-to-end neural voxel rendering called RenderNet. It starts from transforming the input voxel into a camera coordinate. I'd like to quickly emphasize here that such a 3D rigid body transformation is something we actually do not want the neural network to learn because it's very easy to do with coordinate transformation, but very hard for convolution such operation to perform. And we will come back to this later. Having transformed the input voxel into a camera frame, the next step is to learn a neural voxel representation of the 3D shape. What we can do here is to pass the input voxel through a sequence of 3D convolution. Then the output neural voxel contains deep features that is going to be used for computing the shading and the visibility. The next step is to compute the visibility. One might be attempted to basically say, okay, we can use the standard depth buffer algorithm here. But it turns out this is not so easy because when you do this 3D convolution, you kind of diffuse the value within the entire voxel grid. So it's not clear that which grids are from the frontmost surface. At the same time, since every voxel contains deep features, now you have to integrate across all these channels to compute the visibility. To deal with this problem, we use something called a projection unit. This projection unit first takes the 4D input tensor, which is this neural voxel, and reshape it into a 3D tensor by squeezing the last 2 dimensions. The last 2 dimensions are the depth dimension and the feature channel dimension. Then you learn a multi-layer perceptron, which learns to compute the visibility from along the squeezed last channel. So on a higher level, you can think this multi-level perceptron is a inception network that learns to integrate visibility along the both depths and the features. The last step is to use a sequence of 2D up convolution to render the projected neural voxel into a picture. And we train this network end-to-end with mean square error pixel loss. Here are some results. The first row is the input voxels. The second row is the output of the RenderNet. As you can see, RenderNet is able to learn how to do the computation of visibility and the shading. You can also learn RenderNet to generate a different rendering effect, such as contour map, tone shading, and ambient occlusion. In terms of generalization performance, we can use the RenderNet trained on chair model to render some unseen object, such as the bunny and a scene with multiple objects. It can also handle data with corruption and low resolution. The first row renders an input shape that is randomly corrupted. The second row renders an input shape that is, has a resolution that is 50% lower than the training resolution. The RenderNet can also be used to render texture models. In this case, we learn an additional texture network that encodes input texture into a neural texture voxels. And these neural texture voxels will be concatenated with the input shape voxel in a channel-wise way. And a concatenated voxel is going to be fed into a network to render. These are some results of render texture models. The first row is the input voxel. The second row is the ground truth reference image. The third row is our result from RenderNet. As you can see, that the ground truth image obviously has more sharper details, but in general, the RenderNet is able to capture the major facial features and compute the visibility and shading correctly. As a fun experiment, we try to mix and match the shape and the texture. In this example, in the first row, the images are rendered with the same shape input voxel and a different texture voxel. The second row is rendered with the same texture but different shapes. Okay, now let's move on to 3D point cloud. 3D point cloud is actually not so friendly to neural networks. First of all, the data is not arranged on a grid structure. In the meantime, depends on how you sample points from the surface, the number of points and the order of the points can also vary. I just want to quickly point out this recent work called neural point-based graphics from, I think it's Samsung AI Lab. But before we talk about that, let's first talk about how conventional rasterization is done for 3D point clouds. Basically, for every point in the 3D scene, we project the point into the image as a square. And the size of the square is kind of inversely proportional to the distance of the point to the image. Obviously, you have to impose the projected square on top of each other based on depth too. Next, what you do is you try to color the squares using the RGB color of the 3D points. However, if you do this, there's a lot of holes in the result. In the same time, you can see a lot of color blobs. So what these neural point-based graphics did is they replace the RGB color by a learned neural descriptor. This neural descriptor is sort of an 8-dimensional vector that is associated with each input point. You can think about it's a deep feature that compensates the sparsity of the point cloud. This is a visualization of the neural descriptor using the first 3 PCA components. We start by randomly initialize these neural descriptors for each point in the scene and optimize for that particular scene. Obviously, you cannot use the descriptor of one scene to describe another scene, so this optimization has to be done both in the training and the testing stage for each scene. And then the authors use a autoencoder to encode the projected neural descriptor into a photorealistic imaging. This render network is jointly trained with the optimization of the neural descriptor during the training, but can be reused in the testing stage. These are some results which I think is really amazing. The first row is the rendering with conventional RGB descriptor. The second row is the rendering with the neural descriptor. As you can see, there's no hole, and the result is, in general, much sharper. And the very cool thing about this method is the neural descriptor is trained to be view invariant, meaning once they are optimized for a scene, you can render the scene from different angles. That's really cool. Okay, last, we have these mesh models, which is difficult for neural networks because of its graphical representation. I just want to quickly point out these 2 papers. The first one is called deferred neural rendering. It actually uses a very similar idea as we just talked about, which is in this neural point-based graphics. They use very similar ideas, but this paper applies the idea to render mesh models. Another paper is neural 3D mesh render. It is cool in a way that you can even do 3D step transfer. However, the neural network part of this method is used mainly to change the vertex color and the position. It's not so much into the rendering part. But I just put this reference here for people who are interested. Okay, so far we have been talking about the forward rendering. Let's move on to the inverse rendering. Recall the inverse rendering is the problem that given some input image, we want to work on the 3D scene that was used to generate this image. The particular method I'm going to talk about today is called differentiable rendering. It works as follows. First, we start from target image. Then we generate some kind of approximation of the 3D scene. This approximation does not have to be very good. As far as we can render it, we can compare the result with the target image. And then we can define some metric to measure the quantitatively measure the difference between the render image and the target image. And if the rendering process is differentiable, we can backpropagate the loss to update the input model. And if we iteratively do this, eventually the hope is the input model will converge to something meaningful. And the key point here is the forward rendering process has to be differentiable in order to calculate this backpropagate operation. And this is where we immediately see the value of neural networks, because modern neural networks are designed to be differentiable, designed to perform this backpropagation. So we got the gradient for free. Another reason for neural network to be helpful here is, as you can imagine, this iterative optimization process is going to be very expensive. So what we can do with a neural network is to learn a feed-forward process that approximates this iterative optimization. For example, we can learn an autoencoder which encodes the input image into some sort of a latent representation that enables some really interesting downstream tasks, such as novel view synthesis. However, in order to let the encoder to learn the useful representation, we need to use the correct inductive bias. And one inductive bias I'm very interested in, very excited about is like that learning can be a lot easier if you can separate the pose from the appearance. And I truly believe this is something humans do. This is my 4-year-old son playing shape puzzle. The task is to build a complex shape using some basic shape primitive, such as triangle and square. In order to do this task, he has to apply 3D rigid body transformation to these primitive shapes in order to match what is required on the board. It's amazing that humans can do this work rather effortlessly, while this is something the neural network was invented to suffer with. For example, the 2D convolution, or the convolution is a local operation, which there's no way they can carry its global transformation. Fully connected layers might be able to do this, but at the cost of network capacity, because it has to memorize all the different configurations of the same object. So we ask the question, how about we just use simple coordinated transformation to encode the pose of the object and separate the pose from the appearance, whether that will make the learning easier. So we try this idea called HoloGAN, which learns a 3D representation from natural images without the 3D supervision. Without the 3D supervision, I mean there's no 3D data, and there's no ground truth label from the pose of the object in the image during the training process. Everything is learned purely from 2D unlabeled data. So the cool thing about this idea is the learning is driven by inductive bias as opposed to supervision. Let's first take a look at how conventional generative network works. For example, conventional generative networks generate images use 2D convolutions with very few assumptions about the 3D world. For example, this conditional GAN concatenate pose vectors or apply feature-wise transformation to control the pose of the pose of the object in the generated images. Unless ground truth label is used in the training process, the pose is going to be learned as a latent variable, which is hard to interpret. At the same time, using 2D convolution to generate the 3D motion will generate artifacts in the result. In contrast, HoloGAN generates much better result by separating the pose from the motion. This is some random faces generated by HoloGAN, and I'd like to emphasize there's no 3D data used in the training process. And the key point here is HoloGAN used a neural voxel as its latent representation. To learn such neural voxels, we use a 3D generator network. And the learned 3D voxel is going to be rendered by RenderNet, as we just talked about. The 3D generator is basically an extension of StyleGAN into 3D. It has two inputs. The first one is a 4D tensor, a learned 4D tensor, a constant tensor, which is learned as a sort of template of a particular class of object. And this tensor is going to run through a sequence of 3D convolution to become the neural voxel representation. The second input is this random vector used as a control, used as a controller that will be first transformed into a fine parameter of the adaptive instant normalization layer all through the pipeline. Generate the learned 3D voxel representation is going, as I said before, it's going to be rendered by RenderNet. And then in order to train this network in an unsupervised way, we use a discriminant network to classify the render image against real-world image. The key here is it is crucially important that during the training process, we have to apply random rigid body transformation onto this voxel representation. And this is actually how the inductive bias is injected during the learning process. Because in this way, the network is forced to learn some very strong representation that is unbreakable under arbitrary pose. And in fact, if we do not apply random transformation during the learning process, the network was not able to learn. These are some results. As you can see, HoloGAN is pretty robust to view transition and also complex background. One limitation of HoloGAN is it can only learn pose that exist in the dataset, in the training dataset. For example, in this car dataset, there's very little variation in the elevation direction, so the network cannot extrapolate. However, when there are enough training data, the network can surely learn. For example, we use ShapeNet to generate more poses for chairs, and the network is able to learn to do 180-degree rotation in the elevation. We also try to network with some really challenging dataset. For example, this bedroom dataset. This dataset is very challenging due to the fact that there's a very strong appearance variation across the dataset. You can hardly find two bedrooms that looks like each other from different views. In this sense, there's a very weak pose signal in the dataset. However, the network is still able to generate something reasonable, and I think that's really interesting. Another surprise is the network is able to further decompose the appearance into shape and texture. As a test, we feed two different control vectors, one to the 3D part of the network, the other to the 2D part of the network. And it turns out the 3D controller, the controller fitting into the 3D part of the network controls the shape, and the controller fitting into 2D part of the network controls the texture. So these are some results. Every row in this image using the same texture controller but a different shape controller. Every column in this image using the same shape controller but different controller. I think this is truly amazing because it always reminds me about the vertex shader and the fragment shader in a conventional computer graphics pipeline, where the vertex shader changes the geometry and the conventional shader doing the coloring. Okay, I think it's probably a good time to start to draw conclusions. At the beginning of this talk, we asked the question, can neural network be helpful to forward rendering and inverse rendering? And I think the answer is yes. We have seen neural networks being used as a sub-module to speed up ray tracing. And we have seen example of the value-based approach and the policy-based approach. We also have seen neural networks being used as an end-to-end system that helps 3D rasterization. And as far as the inverse problem goes, we see neural network can be used as a very powerful differentiable renderer that opens the door to many interesting downstream applications such as view synthesis. And the key thing here is neural network is able to use the correct interactive BIOS to learn a strong representation. And before I finish the talk, I just want to say this is pretty much still a opening question, a very new research frontier. There's a lot of opportunities. For example, there's still a huge gap between the quality of the end-to-end rendering and the conventional physical-based rendering. And as far as I know, there's really no good solution for neural-based mesh renderer. And in terms of the inverse problem, we have seen encouraging results of learning strong representation. However, it's interesting to see what more effective interactive BIOS and the network architecture can be used to push learning forward. And before I end the talk, I'd like to thank my colleague and collaborators who did an amazing job on these papers, especially two who did the most work for RenderNet and HoloGAN, and also Bing, who did the most work for the neural multicolor denoising. Okay. With that, I finish my talk. Thank you.